Hello everyone, my name is Khanh. I'm doing a PhD in Nautical Operations at UIT, the Arctic University of Norway, and I'm very pleased today to present to you our research work for the IFAC CAMS online conference. The title of the presentation is Development of a Life Cycle Cost Framework for Retrofitting Marine Engines towards Emission Reduction in Shipping. The authors of this work are me, Dr. Lokukaluge Perera from UIT, and Dr. John Emblemsvag from Norwegian University of Science and Technology. This is the scientific content I'm planning to cover. I'm going to start off with the background research problem, and then I will bring to your attention to the research focus, where I'm giving you an overview of the SEATECH project. After that, I will focus on the main core of this study, which is the life cycle cost analysis, LCCA, on marine engines. And finally, I will wrap up with the conclusion. Background research problem. Air emissions from shipping. According to the fourth IMO GHG study, greenhouse gas emissions from shipping increased by approximately 10% from 2012 to 2018. It could represent 90 to 130% of 2008 emissions by 2050, considering possible long-term economic and energy scenarios. If international shipping were a country, it could be the sixth largest producer of GHG emissions. Apart from that, it is a contributor to global sulfur oxides, SOx, and nitrogen oxides, NOx emissions at the figure of 10 to 10% and 15 to 30% correspondingly. It emits as much NOx as the entire EU's remaining emissions combined. So, given the GHG emissions, the International Maritime Organization (IMO) has set out an initial IMO strategy on reducing GHG emissions from shipping. So from this figure, there are two time milestones that should be considered. The first one is 2030, and the aim is to reduce annual CO2 emission per transport work by at least 40% compared to 2008 levels. And the second one is 2050, and the aim is to reduce annual GHG emissions by at least 50% compared to 2008 levels. With regard to drivers of the studies, they can be divided into mandatory and non-mandatory regulations. Air pollutants like NOx, SOx, and PM emissions are addressed in MAPOL Annex 6, Chapter 3, specifically Regulation 13 and 14. Global Sulfur Cap 2020 were already entered into force, limiting the sulfur content in bunker fuel to 0.5%. GHG emissions are addressed in MAPOL Annex 6, Chapter 4 with two measures. Technical measures with EDI for new vessels, EXI for existing vessels, operational measures with SAM for existing vessels. And I already mentioned before regarding the initial IMO strategy on GHG reduction. There are two regimes regarding data-driven regulations. The IMO DCS data collection system, and the EU MRV monitoring, reporting, and verification. In terms of sustainability driver, the UN 2030 agenda was released by the United Nations with 17 sustainable development goals. And goal number 7, affordable and clean energy. Number 12, responsible consumption and production. And number 13, climate action are relevant to the scope of this study. Financial concern regarding volatile fuel price and rising costs and competitive market are seen as business drivers. Well, putting the whole into a big picture, I would say that it is a big challenge since, as you can see in this picture, there are numerous factors that the maritime industry is facing with towards decarbonization. How to achieve the ambitious targets I mentioned before? Well, there are three main ways to do that. The first one is opting for alternative fuels and energy sources like utilizing LNG, methanol, or ammonia, or other alternative fuels. The second one is improving technical efficiency. This can be done by introducing new technology with higher efficiency. The third one is improving operational efficiency. And there are several options under this. For example, weather routing, space optimization, and vessel performance reporting, so on and so forth. Research focus, SEATECH project. The research study has been conducted under the SEATECH project, and it is an EU-funded project with the aim to develop two innovative technologies. The first technology is the renewable energy-based propulsion innovation. It consists of a biomimetic dynamic wing mounted at the ship bow to augment ship propulsion in moderate and higher sea states. It will capture wave energy, produce extra thrust, and damp ship motions. The second technology is the dual fuel engine innovation, and it is based on the idea of achieving ultra-high energy conversion efficiency by precisely controlling the combustion process. So, with the high efficiency and the utilization of clean fuel, which is the LNG, running this engine will result in extremely low exhaust gas emissions. So the whole ideas of this project is to combine these technologies so that now we will be able to achieve a great increase of fuel efficiency and radical emission reductions. Life cycle cost analysis (LCCA) on marine engines. So our responsibility under the SEATECH project is to conduct the life cycle cost analysis on bunker fuel, on engine technology, and on propeller technology. But the main focus at the moment is to conduct the LCCA on engine technology, and it is also the scope of this study. In order to do that, we need to obtain industrial data and data from other sources. Domain knowledge would be beneficial throughout the LCCA, and the expected outcome would be economic key performance indicators, KPI, considering total cost performance and technology investments. So it could be a decision support tool that is useful for ship owners throughout the design or retrofitting phase of the vessel. We have defined a framework for the LCCA, starting with problem definition, where we have defined the scope and the objective. After that, we have identified cost elements under breakdown analysis. For the cost modeling, we have selected cost estimation methods, and we are also collecting data. Then we will deploy our model for cost estimates, considering cost treatment, for example, time value of money. In the evaluation phase, we will conduct sensitivity analysis for uncertainty and risk handling. We will also develop economic KPIs as indicators of comparisons. Then in the end, the result will be reported. The LCCA framework is based on the cradle-to-grave perspective, ranging from construction, operation, maintenance, to end of life. There are three main cost estimation models in the literature. Regarding the analogous cost estimation model, it is characterized by adjusting the cost of a similar product relative to differences between it and the target product. For the parametric cost estimation model, the principle is to derive the product's cost through cost estimation relationship based on historic cases. Regarding the bottom-up cost estimation model, which is the engineering type model, all work steps with their cost for material, component, operation, maintenance, and disposal are added up to produce the final cost. And in this study, we are utilizing the engineering type model, but we are combining it with the others when the data will be unavailable at some points. Given the proposed framework and the bottom-up model I mentioned before, we have defined a tree structure for the life cycle cost of a diesel engine. And this is the base case for comparison, because we would like to compare the total cost performance of this diesel engine with that of the SEATECH engine. And we were looking into a case ship with this diesel engine for our analysis. And this table shows several specifications of this ship and its engine. Regarding the construction cost, we have defined an engine breakdown structure. And as you can see in this table, we got some sort of main engines components and systems, along with the associated cost range. And on average, the construction cost is determined approximately as 940k euros. Okay, so we were looking into the operation cost of this diesel engine, and what we did is we were trying to calculate the fuel oil consumption and lubricant oil consumption based on this equation. And in each mode, we need to find out the power required, the specific fuel oil consumption, the specific lubricant oil consumption, and the operating hours. So we go looking into the ship's operation profile, and the ship was operating under three main engine modes here, along with the associated operation hours, the speed, the power, and the engine load. So we need to obtain the specific fuel consumption in each mode here. So what we did is we were looking into the table here based on the technical file of this engine, and we did some sort of interpolation and extrapolation so that we can come up with the specific fuel consumption in each mode. So we will be able to calculate the fuel oil consumption in each mode, the lubricant oil consumption in each mode yearly. So here the figure shows the relative specific fuel consumption as a function of the relative engine load, and the minimum value of the SFOC here is located at the relative engine load of 75%. So maintaining the engine loads around this point is required in order to minimize the fuel oil consumption and optimize the engine performance. So from what we found in terms of annual fuel oil consumption and annual lubricant oil consumption previously, we can calculate the cost and come up with the annual operation cost here. And we were looking into the net present cost of this operation cost based on this equation, and with discount rate and inflation rate in this table. So we got the results for the NPC here. Also, we did some sensitivity analysis in different scenarios with the change of discount rate and inflation rate, and this is the result we got for the sensitivity analysis. Conclusion. So this is the first step towards enhancing our understanding of economic impacts on retrofitting investment in a marine engine throughout its lifespan, and the results indicate that the operation hours and the engine loads are major contributing factors in determining the operation costs, thereby influencing the total life cycle cost of the engine. And the proposed framework is useful for ship owners in making retrofitting decisions regarding emission reduction. On the other hand, the proposed framework requires intensive data gathering and collection. In terms of future work, we would like to do the cost calculation for the maintenance and the end of life phase, and we need to collect more data so that we will be able to conduct a comparative study between the diesel engine versus the SEATECH engine with regard to the total cost performance, and we will do the evaluation considering the economic KPIs, and we will do the sensitivity analysis in order to handle the uncertainty and the risks. Thank you.